Okay, so lesson 11.4, last lesson of the chapter where we're talking about waves. And we're going to be talking about the properties of light. And there's a lot of information here about light. So try your best, take your notes, pause if you need to. But just a warning, there's a lot of information here. So the first thing is something you're familiar with, the idea of reflection, right? So light, you saw in the video from last lesson, can behave as a particle, meaning it's allowed to bounce off stuff, but it can also behave like a wave, which means it can travel and hit things, sometimes even going through them. Reflection is when that light wave actually bounces off an object, right? And so you can see this happen with sound waves, and you can get things like echoes. You can see this happen with light waves, and you can get things like mirror reflection. So reflection, literally just bouncing a wave off of an object. Now, there's a lot of words here, but all I really did was describe what this picture is over here. So if you write the first line and you draw this picture, you should be good. So basically, we have something called the law of reflection. And what that means is whatever angle that light ray strikes the object, it's going to bounce off at that exact same angle. So the original light beam that hit the object is called the incident beam. This picture calls it the incident ray, same thing, right? And so the angle that that incident beam struck the object is called the angle of incidence. When it reflects off, that is called the reflected ray. And that angle is the angle of reflection. And if you look at the picture, you can see that they're the same, right? That normal line is a beam formed right in between those two. So halfway between the angle of incidence and the angle of reflection. So that's the law of reflection. Now, refraction is a little bit different. If you've ever stood in a pool and you've noticed that like your legs seem like they're bending or they're like off center from your body, that is because of refraction. Um, we talked about how waves can travel at different speeds depending on what the type of matter is, right? And medium is another word for that matter. Light does the same thing. So light can travel faster through different mediums or different materials, right? So if it's traveling at one speed in the air and then it hits the water, now it's traveling at a different speed. That's why you start to see a distorted or bended kind of a picture. So literally all refraction is bending a wave because the speed of the wave changes from one medium to another. So we have something called the index of refraction. Every material has an index of refraction. Basically, this is just a value that tells you how much the speed of light will change in that material. So now diffraction. So if you think back to when we were studying the different types of light sources, back when we were looking at we used the spectroscopes. Remember when we were pointing them at the different types of light bulbs? That was like an example of diffraction. Diffraction is taking a wave and basically bending it through or around something. And a lot of times that will cause it to spread out. So just the bending of a wave because of the speed through different materials is refraction, but diffracting is when the light wave actually bends through or around something, causing the wave to spread apart. So now a little bit about mirrors and lenses. So you have two main categories, and you have the same categories for the lenses. You have this picture in your book too. So you have concave and convex mirrors. Basically, it just depends on the way that they are curved. So concave mirrors basically cause objects to appear more magnified, where convex mirrors allow things to appear smaller and farther away. That's the main thing that you need to know. You don't need to know a whole lot about how it affects the focal point, but if you can explain how concave and convex mirrors affect a reflected image, and if you were given a diagram, could you label one convex and one concave, then you're good. Next, we have concave and convex lenses. Now, concave lenses are thinner in the middle than they are at the edges. Typically use these in a lot of optical equipment, so things like telescopes, cameras, microscopes. Convex mirrors are usually used to magnify objects, so like contact lenses. These are thicker in the middle than they are on the outside. So just like with the mirrors, if you can explain um, how they affect an image, and if you were given a diagram, could you label one concave versus the other convex? Now we have prisms. So prisms work just like our spectroscopes did. You have some wavelength of light hitting it, and then it breaks apart all the different colors because they have different wavelengths. And that's exactly what it did when we were looking at the spectroscope to kind of see what different colors were in there. So white light is composed of all the visible light spectrum that we can see. So all of those colors. A prism basically breaks them apart based on its wavelength. I wish we could have been at school. I had some prisms we could play with, but you can look up some videos of how some work. Now, some waves interact in different ways. One way that waves can interact is called constructive interference. And think of what does constructing mean? It's like building something, right? So if you have two waves, here we have the yellow and the blue wave, wave one, wave two. And if their crests and troughs line up, doesn't have to be the exact same amplitude, but like if they're at the exact, like relatively same place, like similar wavelengths, they can build up together to form a larger wave. So they're constructing a larger wave by overlapping. That's where that green wave came from. Destructive interference is kind of the opposite. So now we still have our yellow and our blue waves, wave one and wave two, but you notice that the crests and the troughs are opposite this time. So they're not actually going to line up and build up. They're going to subtract from each other, making the waves smaller. So you see the green wave is actually smaller than the yellow wave now. That is destructive interference. So then we have color. So you may have heard people say like, oh, well, black is actually the absence of color. It's not a color. Um, that is true, but it also depends on if you're talking about colors of light or colors of pigment. So we're going to start by talking of colors of light. So colors of light come from that visible light spectrum that you just learned about, right? All those different colors of light that we can see. And white light, when it strikes something, it has all those colors in it. And the colors that you see are the ones that are reflected. So this leaf here is an example. So the white light's hitting it. All the colors are being absorbed by the leaf except for the green. So since the green is being reflected, that is what you see, right? So if this were to be something black, that means that all the colors were absorbed and you couldn't see anything. There were no colors reflected. The colors are there, they're just all absorbed. If you were to see white, that means every single color was reflected, right? So that's what happens when you're talking about colors of light. Now you have three different primary colors of light. Write these down. When you put them in your notes, make sure you say that they are primary colors of light because there are different ones for pigment. That is red, green, and blue. You mix up those primary colors of light, you can produce tons of other colors that you see. So now our pigments. Pigments are colored materials, right? So it could be something like a paint, doesn't have to be. But basically, they mix up a bunch of substances that reflect certain lights, right? So if I wanted something pink and I know that these are the colors that reflect the right amount of red that I want or the right amount of white that I want, and then I could mix them together and make a solid pigment. The three primary colors of pigment are red, blue, bluish green, and yellow. We call them magenta, cyan, and yellow. So if you've ever seen like a printer cartridge, it's going to be in magenta, cyan, and yellow. So red, blue, green, those are primary colors of light. Magenta, cyan, yellow, those are primary colors of pigment. And that's it. That's the waves. That is chapter 11. Watch the videos that I left for you.